Hello, we're team number 14496 Roboctopi. I'm Nico, the team captain and the primary robot designer.
And I'm Sherwin. I'm the primary chassis driver and also programmer.
PowerPlay was our 5th season in FTC, and it was our first time going to Worlds. We actually saw huge success at Worlds this year. We were division champions for the Ocho division with Wolfpack Machina and out-of-the-box robotics. And we also ended the season ranked 5th on FTC stats. So how did we get here? I'll cover some of the hardware innovations that made this possible. Our Freight Frenzy robot was functional in that it could complete all aspects of the game, but it was very complex with lots of different systems. This made it somewhat unreliable because there were many different mechanisms that could break. It was also very difficult to program for optimal performance because of the sheer number of mechanisms that we had to code. So this year we went for simplicity. Outside of the four chassis motors, we have 2 motors and 3 servos on the entire rest of the robot. This made it far easier to control because there's way fewer mechanisms that can fail, which also increased our reliability. However, we don't strive for simplicity at the cost of performance. We pack lots of functionality onto the few actuators that we have. So for example, our intake servo, which opens and closes our claw, has 3 different functions on it. Firstly, it can obviously pick up cones, but secondly, it can also pick up our beacon. So we pick up both the cone and the beacon at the same time, and then we can drop just the cone, switch to a different pole, and then drop the beacon by itself. This allows us to claim 2 different junctions and increases our ability to create circuits in endgame. And then the third function is it can also collect cones that have been knocked over. So we can drive up to them, flip them up, and then intake them like normal. So these 3 different features are packed onto one single actuator on the robot, which allows us to maintain that simplicity. Flexibility is also really important so that you can work well with any alliance partner no matter the randomized match. So this is why we created a small and light robot that can easily navigate anywhere on the field very quickly to any pole. The robot is also fully symmetrical, which allows it to intake both on the front and the back of the robot, as well as deliver on the front or the back of the robot. And this also works for both autonomous and teleop. So this greatly reduces the number of rotations that our autonomous has to do, and as well as our drivers, because we can switch just with a simple toggle button between the 2 states. It is often fastest to move the cone on the shortest path from the substation to the pole that you're trying to score on. And this is why we don't have a transfer on our robot. The intake and delivery system are fully integrated onto one mechanism on the robot. Additionally, we knew that the fastest way to deliver cones was to take advantage of every mechanism on the robot at the same time. So when delivering a cone, the chassis is driving to the pole, the lift takes the cone up to the pole's height, the arm flips the cone to the other side of the robot, and the wrist tilts the cone towards the pole so that we can score even faster. All of these different actions happen at the same time, and there's no mechanism dependencies. This makes our cycle times even faster. Finally, we optimized the weight distribution on our robot. We knew that center of gravity was going to be really important this year to maintain a stable robot because we had such a small footprint as well as a lift that could lift all the way up to the high goal. However, we didn't want to add a dead weight to the bottom of the robot because we knew that would negatively impact our agility on the playing field. So this is why we optimized the weight distribution of the robot, such that the 4 chassis motors are placed as low to the ground as possible, and then the lift motor and the battery are placed right on top of them. This is the majority of the robot's weight, and it's all very low to the ground. And because of this, we were extremely stable this year and never had any tipping issues, even though our robot was the lightest we've ever had it at only 28 pounds. We even optimized the weight distribution of the 6th motor on the robot, which is actually on top of the lift. It controls the arm rotation here. And we used it as a counterweight for the arm so that the motor would have to draw less current when flipping the arm from one side to the other. So as you can see, all of the heavy components on the robot were very intentionally placed to maximize its performance. Now I'll turn it over to Sherwin for the software.
Yeah, so over on our software, actually, this year we had a lot of sensor optimizations. For example, when you're picking up off a cone stack, you don't know how tall the cone stack is. But instead of having to pre-enter that information, we actually use our lift as sort of a sensorless homing system where we press our lift down into a cone stack to detect how tall it is. We also have beam break sensors in our cone pickup area so we can auto pick up once a cone's detected. But I think the biggest thing that we implemented starting this year was a bunch of robot optimizations with our finite state machine. So over on all our slides, you should see a flowchart where we have our robot state, which is essentially a finite list of states that a robot can be in, and a bunch of well-defined connections between those states. And this allows us to predictably control our robot's mechanisms, switching from one state to the other without any weird edge cases as much, and also optimizing the paths between them. Also, another thing we do with our state is control optimizations. For example, our robot's arm starts in the upright position, and once we want to intake a cone, the first thing we do is first bring our arm down to prepare the pickup, and then after that, we actually pick up the cone. And this two-step process could be delegated to two separate buttons, but we actually have one button that does a different thing depending on the current state of the robot. And the good thing about this is, A, you save less, you use less buttons on your controllers. We actually don't, I think we have the least buttons that we have in all our past seasons on our controller. And also the other thing is that psychologically, you only associate one button with getting to the pick up a cone state, which is pretty useful for reaction time. And then moving on from that, another thing we did this season was use a slow-mo camera on our phones actually to optimize our pickup process. Because when you look at the robot in slow motion, you can see where you're losing all your times in delays. And we use that information to parallelize our processes. And even if you just save like 500 milliseconds or something in your transfer, that's a really small amount of time, but throughout autonomous, that adds up. And we were able to shave off a few seconds and increase the amount of cones that we can score with the time we have in auto up to a 1+5 autonomous once it's fully optimized. Now moving on to our vision pipeline. During autonomous, we auto-align to the pole we're scoring on using a camera that's built into our grabber that actually looks through the cone that we're currently holding. And the way this algorithm works is in a few steps. First, we use a flood fill algorithm to take all the yellow pixels in the image and group them into individual poles. And then once they're grouped, we can individually score each of them using a heuristic to figure out which one is the most likely to be the one that's centered and that we're going for, and also not just a random yellow piece on some robot. And then once we've selected a pole, we can calculate the trajectory for it and go for that pole. And we've actually had a few optimizations in this process because in past years, we have had color detection algorithms before. But this year, our algorithm that detects all the yellow pixels is the most advanced we've ever made it, where typically what we used to do was have a set threshold for how yellow something should be to be considered yellow. But this year, we actually don't have a set threshold at all. We use a statistical algorithm to figure out the most significant yellow pixel just to find the yellowest thing, which makes it independent of lighting condition. We also test the colors in the HSV color space, so we can test the hue to be in the yellow region, regardless of saturation or value, which helps with being independent of any lighting conditions, which made us more reliable. Also, another thing is instead of averaging all the yellow pixels in the image to find the center pole to go for, we individually group the poles and target them individually. Because if you were to just average all the pixels, one pole off to the side could shift your average over, and so that wouldn't be necessarily optimal heuristic to use. So instead, using flood fill allows us to look at all the poles individually and pick the best one and then go for that. And yeah, our vision algorithm has been pretty successful this season, and we've been able to improve our auto reliability, and it worked pretty well. And I think, yeah, those were some of the main innovations we've had this season. And we'd love to talk about any more and any questions that you might have.
Yeah, we got a few questions coming in already, everybody. So starting out from FTC Robo Players, they want to know more about your side plates and what they're made of.
Yeah, so our side plates, we use a laser cutter. So these side plates are made out of Delrin. And Delrin is a very strong material, but it can be pretty flexible on plates of this size. And so we use a couple different strategies to make them as rigid as possible. So the first is what we call the sandwich technique. So we basically put two Delrin plates next to each other with a whole bunch of standoffs in between. And this basically has the effect of redirecting the force from one that is bending the plate to one that is compressing and extending the plate. And this is a direction in which Delrin is very strong in, and it's basically allows us to have, for example, our chassis assembly has a plate on each side, and this allows us to make everything really rigid. Another strategy we use to make them very rigid is triangles. Triangles are very strong structures. So you can see our robot is actually kind of one big triangle with the shape of the plate. And then we also have some other internal triangles that brace it in the other axes to use this material.
And also, so Delrin is a plastic, and the reason we use it is that it can be laser cut, like Nico said, which is just a lot easier and faster process than machining something. But yeah, we do have to take more care when using it because it is not as rigid and it's easier to bend. Yeah.
Next question coming in from John Cannon. Wants to see a little bit more about the mechanism for using one actuator to control 3 different mechanisms. Could you elaborate a little bit more on that?
Yeah, so this is our intake claw up here. Let's see. Yeah, you can see that. So our intake claw just opens up and closes like that. So our capstone actually has a special design that allows it to basically hook into the top of this claw. So when we grab a cone with the capstone on top of it, the claw itself is grabbing onto the cone just like normal, but then there's a little hook that allows the capstone to basically attach to the claw itself, so that when we open the claw just a little bit, the claw will let go of the cone and the cone will slip through and score onto a pole. But then the hook on the beacon will still be hooked onto our claw mechanism. And so this allows us to switch to a different pole and then open the claw all the way, and that will release our beacon. And then the third system is, well, it involves more than just that one actuator, but basically we can come down onto a cone like this and then drive backwards, and that allows us to basically tip forward a cone.
All right, we got a couple more questions. Let's go a little bit quicker on them, but from Screen 404 asked, what trade-offs did you have to make in order to use, I'm going to read this phonetically, so hopefully this will be all right. What trade-offs did you have to make in order to use so few actuators?
So it was actually very nice because there's lots less code that you have to do to control all of the systems. And everything is just much easier to control. And then, yeah, there's also, like, for example, on the scissor lift in the back here, we have a whole wiring guide that brings the wires all the way up to the lift system. And so because we have fewer actuators, there's less cables that we have to route up as well. So, yeah.
All right, and last question coming in from Sea Lake Sinton. Was there any feedback given to the drivers from your vision pole detection algorithm, or was this only used for autonomous?
We initially did try to add a button that would automatically align the robot to the pole during driver control, but we actually found that the driver, which is Sherwin here, could align to it much faster than the vision could during teleop. So we removed that feature and we align only manually.
Yeah, I think the poles being compliant and you just being able to push the cone into them meant that it's not as important for the driver stage when you're just driving up to the cone as auto.
Yeah, and we also have a wrist mechanism that tilts the cone towards the pole. So this eliminates one axis of alignment, and so it's much easier for both autonomous and the drivers to align to a pole.
All right, 14496 Roboctopi, thank you so much for telling us more about your team, and congratulations on a fantastic season. And good luck in Center Stage coming up very soon. Thanks a lot, guys.
Thank you so much.
Thanks for having us.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. At Kettering University, over 30% of the student population was in high school robotics. These same students have received a portion of over $7 million in FIRST scholarship. Scholarship applications will open in September. Get ready to go pro and get more information at kettering.edu/first. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.